Right, so then it means it's 70 megawatt. Divide by square root 3, divide by 13.8. Times 10 to the power of 3. And you get your power. Okay.
2928,59.
2928,59. Okay. Now, remember we start with the drawing always. There's V. There's E. And E is 1,67 times V. Phase, ne? We've got 30 degrees there. A lagging current. Then we've got IQ and ID with an angle phi. Right.
Yes.
Okay. So now that means this will be ID XD and IQ XQ. Now we're sitting with a problem. First of all, let's draw this line here.
Sir,
Yes.
that ID XD shouldn't it be IQ XQ because of its perpendicular to IQ that the ball drop.
Is ID XD and IQ XQ. Or is that not what you mean?
Asking, you see on that phasor, which is the armature current phasor. What is the current which is in phase with it? Is it not IQ?
No, remember IQ lies there.
Okay.
ID lies there.
Okay, all right.
So now IDXD must lead this voltage. This voltage leads this current.
Yeah.
All right, so now we can calculate this part here. That will be V cos 30. Because that's 90 degrees. We've got V, we've got the angle. All right? So then we can say that ID or IQ XQ is equal to V cos 30. So that is 13 divided by square root 3, which is 7978, I think. Divide by square root 3 times cos 30. And IQ is then divide by XQ. And then you will get your IQ.
KID 6,900.
All right, come again?
6.9 kilo amps.
1 point?
No, 6.9 kilo amps. IQ.
6.9. Are you sure?
No.
6.9?
No, I'm not sure. 6,900.
Okay. Let me check. Hey. XQ is 1.33, né? 5176. Comma 3.
Okay.
And then ID, XD Now, this is E.
Should be sine.
So this part here will be E minus
Minus
V cos 30.
ID XD.
You agree? Because we've got E and we've got V cos 30. And you see that?
Yes, yes, yes.
Right, so then we can calculate ID. 1.67 times
With an angle of 30.
Sir,
uh,
your IQ XQ is equals to V sine 30, not cos.
yeah, right, fine. I thought you said you're not going to say.
Good evening, Lavu.
Huh?
Good evening. Can you please record the video?
Yes, I'm doing that.
All right, thanks. What question is this?
For exercise 4, number 5.
For number 5, all right. Thanks.
One, 6, 7 times. That is, oh man, 7, 9, 6, 7, 4, 3 minus 7, 9, 6, 7, 4, 3. Divide by 2.38. I get 242, 2242, 93.
You forgot the cos 30.
Aye, man. Una.
Yes, I'm here.
All right, what's the answer then?
2691.435.
206.
2691.44. 44. Sharp.
Oh. Right. So now we can calculate the current. IA is equal to IQ minus
Sir,
ID.
when we write IQ, the right value for IQ is 2995.28.
299528. Okay. So that gives us 2995.28 minus J2691.44. That gives us
4026,
4026.
85.
85 angle.
Angle of minus 41.94.
Right.
Yeah.
Now we have to calculate the power. So,
Sir, can you use another method
no, why?
to get IA? Because I want to check something.
Double check something.
Can you use one those two formulas for then alternate it legally? ID equals to IA sine of
None of what?
power factor plus load angle.
Yes.
I want us to use this one to get the power factor.
Yeah, but how? You don't have phi.
So you have ID, you have IA, you have load angle, which means you can get the power factor.
Yeah, the power factor is now 30 plus 41.94. Cosine of that.
Yesterday you said when you get that one, you minus or you add with and load angle. That one is not a power factor. You said so.
So what's the power factor? Is that what? Yeah.
Power factor is 5.
And we calculated this whole angle. Do you agree?
Yes.
You add with that.
So therefore, phi is
Now
then
you minus.
41.94 minus 30. That gives us 11.94. Okay,
Okay.
right. Then develop power. We developed this EV over XD sine delta plus V squared XD minus XQ over 2 XD XQ sine 2 delta. So E is now, how much was E? 13.
It's 13305,615.
1330.
05,615.
Okay, 62. Times
Sure.
7967,43.
443. Yeah.
Divide by XD, which is 2,38.
2.3. Yeah.
And then sine 30 plus 7967,43 squared
Squared
2.38
over 2.
minus 1.33 over 2 times 2.38 times 1.33 sine 60.
Sir, can I ask something? Is it okay if we use per unit and then convert everything else once you're done? Because I find it simple to do my calculations in per unit and then convert my final answer into actual.
You can do that, but sometimes it's longer to do that, and you need to use your time effectively when you're writing a text. So always do the shortest route. Does that answer your
Oh,
question?
okay. Yeah, because normally I make mistakes when I punch into my calculator if there's so many numbers, and if it's in per unit, it's quite simple to do it.
Okay. I've got no problem with that, as long as it's right. Okay. So what do you get that answer?
Okay, it's per phase.
Yeah,
31.389 megawatt per phase.
389. Okay, and that is total?
Yes, multiply by 3, it's 94,168.
All right. Then the reluctance torque. So first of all, we calculate P reluctance, which is V squared XD minus XQ over 2XD XQ sine 60. That is 796,743 squared 2.38 minus 1.33 divided by 2 times 2.38 1.33 sine 60, and then you get a value there. Now remember, as we are going, going to use total,
3.
so therefore it must be times by 3.
27.354.
After you've
Uh,
multiplied it by
Megawatt. 27.
okay, okay, yeah, yeah.
27, 335 megawatt.
okay. Right. So now torque is going to be P reluctance over omega. So that is 27.35 times 60 over 2 pi, and it's a 40 pole, so it's 2,000
By 150.
is 150, yeah?
Yeah.
And then you should get your 1.74 meganewton.
1. Do you want the answer?
Sorry, so
I thought you
how
had
do you
it.
get the 150?
That is 3,000 divided by the number of pole pairs. Hey man, that is stuff that you've done in engineer machines too.
Is it not 1.74?
But so where do you get the speed from? Because in the
Yeah.
question they don't give speed.
Hey,
And in the theory they talk of 1.5 and 3,000.
F is empty over 60, so therefore N is 60F over the pole pairs. Normally, if we don't give frequency, it's 50 hertz. So that's 3,000 divided by 20.
So say what will happen if you don't give us frequency, then I assume 50 years.
Yes, because we're in South Africa.
Correct.
Sometimes you can assume 0.
0.
Yeah, that's when we have a power cut.
Oh, okay.
All right.
So yeah, before you can continue on that one, actually, you see on that reluctant torque, Ankere is responsible for running our alternator when we don't have E. Even if we don't have E, if E is 0, the alternator will still turn because of that reluctant torque.
Yeah, but it won't start.
It don't start, but it will just run.
Yeah, if it the reluctance torque is bigger than our losses. If it's less than that, then it'll stop.
In relation to that, so can I ask something?
Yeah.
When you say to us that once the excitation has been switched off, right, and then we should calculate the developed power. So now, does that mean that the excitation part of my of my formula, I remove it and then I just calculate developed power in terms of reluctance?
Yeah. Yeah.
So,
Don't
sir,
talk
because
about developed power anymore. Now it's reluctance power.
yeah, because I think there is a question that you asked something like that in the tutorial, whereby you said that what happens when we switch off the excitation, right? So now the question that I have, sir, is that when calculating your load angle, right? Because you're gonna need load angle even though you do not have excitation anymore. So now, do you still go through the route of calculating E? Because now,
No.
in essence,
Okay,
how do you do it?
Then normally you will get maximum power with 45 degrees there. So that is V. And then you've got your that will be your PR, and that will be Q. That will be IQ, and that will be ID, and that is 45 degrees. And that is phi. So now, normally we say delta is equal to 45 degrees because 2 delta is going to be 90. So therefore, delta will be 45. And then we can calculate the current. Okay.
Okay. Also, delta in this case is 45 degrees when my excitation is switched off.
Yeah, because normally then it will run at maximum.
Oh, okay.
All right, then something else. When you calculate P develop, that part, write it down. And the same with this part. Because you're going to use it when you calculate delta max. This must R cos K1 minus K1 over 8K2 plus the square root of minus K1 over 8K2 squared plus 0.5. So this part here is K1 and that is K2. So once you've got that, write it down. Otherwise, you have to calculate it again and again and again. Okay.
Another question, sir.
Hmm.
Let's say, for example, on the question of when excitation is switched off, but you've also given me R. I have R. So when I calculate my new developed power, do I also add the 3I squared R as well,
Yes.
along with the rotational losses?
Yeah.
Oh, okay.
Because you still got the current flowing.
Mm-hmm.
And therefore it will be I squared R.
Oh, okay. So what is it meant when what does the term saliency mean?
Sticking out.
Sir?
Remember, for a cylindrical rotor, all
Mm-hmm.
the components are inside. Yeah? But for a salient pole, we have this. And salient only means sticking out.
So when I'm asked to calculate the power due to saliency, so I'm just calculating what developed power.
Yeah.
Oh, okay.
Oh, time flies when you're having fun, huh?
Sir?
I say time flies when you're having fun. We've only got 9 minutes left again. Okay. Any more questions?
Sir, I have another one. What is the magnet power due to saliency the same as when I'm asked power due to saliency?
Yes, the same thing.
Oh, okay. And then, sir, could we kindly do question 3 in the tutorial?
What does it say? I don't have it with me here. No, I don't have.
It's saying 15 MVA, 12 kilovolts, star connected salient pole motor with reactance XD of 1,2 per unit and XQ of 0,6 per unit. And then it says ignore rotational and copper losses. The machine's load is varied to meet the following condition: maximum power with no field excitation. And then the question is estimate the value of this power, the armature current, the power factor of this condition.
That's basically what you just discussed here.
Mm-hmm.
Because we don't have anything else. So we're going to say that the power is the reluctance power, which then will be V squared xd minus xq over 2xd xq, and it will be 45 degrees because it's doing maximum power at that stage.
Mm,
And then basically,
okay.
this is your phasor diagram. Now, Ona asked, but this is lagging. Now, most books use the same thing, but I would say lagging power factor for a motor is this way, and therefore for an alternator is downwards, for a motor it's going to be like that. So IQ and ID will lie there with your 45. Still, that will be your lagging power factor, leading power factor. Okay.
Okay, sir.
This will be
Sorry, sir. Is the video recording?
yes. Bye.
So basically, sir, after I've calculated my sir, because I'm asked to calculate the armature current, can I just use the formula for S over root 3 multiply by my
No,
V terminal?
no, it's only because you've got the reluctance power. So this current, you're going to say that ID, XD is equal to IQ, XQ is equal to cos of 45, which is 0.7071. And from that, you can say ID will then be 0.717 or 7071 divided by XD, which is 1.2. And IQ will be 0.7071 divided by 0.6. Then you can calculate the current. Including,
Okay, sir.
okay.
Yes.
All right. Any other questions here?
Question 8.4.
I still haven't got to that one.
Okay.
And remember that number 9, just leave it out. Like Ona has discovered, it is something of another kind. It's above your pay grade. Just scrap it completely.
Number 9 of exercise 4.
Pardon?
You see the number 9 on the same exercise, exercise 4.
Yeah, you can leave it.
It's number 9 at exercise, and then in tutorial, it's question 3. The one Rebecca was asking is the same as number 9.
All right.
Okay. You try it and just to see.
Sir, and when I'm asked to calculate, because this is where I need clarity on as well. When I'm asked to calculate the developed power of an alternator, is it the same as calculating developed power of a motor, mainly because I do not have, R is not given?
Yeah.
So when R is given, then for my motor, my developed power is going to be the copper losses. I'm gonna add the copper losses.
Now you're gonna subtract it.
I'm gonna subtract
Yeah.
to get my, now I'm getting what my output power.
No, remember for a motor it's the other way around. Yeah, this developed power is going to be inside of your stator.
Mm-hmm.
So if you want, it's good. Yeah. No, I think you just leave it out, so just like that. And then when you calculate the output power, you subtract I squared R.
All right, sir.
Okay. So we go over to design. Oh, yeah, well, we've got 2 minutes left. Any more questions there?
Design.
Then guys,
Just now.
I have questions for tomorrow on design.
Sir, I have questions. No, Warren.
Yeah,
I have questions. I
come
want
with them.
to solve them tomorrow. I don't. Sir, I
No,
have
come with
questions
them.
for design.
Yeah,
Yes,
yeah.
ask them.
I agree. He's saying is 2 minutes left.
No, I'm gonna come in again. I must
Yeah.
just
Okay. Okay, sir. Sir,
yeah.
answer for exercise number 3. The one that you said I must calculate the actual. Is that the actual? Still not correct. Oh, the D and the L. The measurements.
Yeah.
I used 0.6, but I didn't get the answer.
Ah,
I don't know what's the problem.
it's probably you that's the problem.
The problem.
Yeah. You ask too many questions.
Oh, what's the I didn't ask any famous.
They say a fool can ask more questions than a wise can answer. How's that?
I don't know.
Yeah, we're gonna lock in just now again. I wish I had a license for this bloody thing. But the university, they don't want to buy one.
By one, we are on the 4th industrial revolution.
Pardon?
I'm saying we are on the 4th industrial revolution. They should buy one. We should normalize distance learning.
Yeah, they say no, they use Teams.